Welcome to Transmission Media and Antenna Systems. In this lesson, we'll talk about transmission line basics. Transmission lines in communication carry telephone signals, computer data in LANs, TV, and internet signal in cable TV system, and signals from a transmitter to an antenna, and from an antenna to a receiver. Transmission lines are critical links in any communication system. They are more than pieces of wire or cable. Their electrical characteristics are critical and must be matched to the equipment for successful communication to take place. Transmission lines are also circuits. At very high frequencies, where wavelengths are short, transmission lines act as a resonance circuit and even reactive components. At VHF, UHF, and microwave frequencies, most tuned circuits and filters are implemented with transmission lines. In this lesson, you'll be able to name the different types of transmission lines and list some specific applications of each. Explain the circumstances under which transmission lines can be used as tuned circuits and reactive components. To define characteristic impedance and calculate the characteristic impedance of a transmission line by using several different methods. And lastly, to compute the length of a transmission line in wavelengths. The two primary requirements of a transmission line are that, first, the line introduces minimum attenuation to the signal, and two, the line does not radiate any of the signal as radio energy. All transmission lines and connectors are designed with these requirements in mind. Shown are the common types of transmission lines. A parallel wire line is made of two parallel conductors separated by a space of about 1/2 inches to several inches. As you can see, there is a two-wire balance line in which insulating spacers have been used to keep the wires separated. Such lines are rarely used today. A variation of parallel line is the 300 ohm twin lead type shown, where the spacing between the wires is maintained by a continuous plastic insulator. The most widely used type of transmission line is the coaxial cable, which consists of a solid center conductor surrounded by a dielectric material, usually a plastic insulator such as Teflon, as shown. The major benefit of using coaxial cable is that it is completely shielded so that external noise has little or no effect on the communication signal. Twisted pair cable, as the name implies, uses two insulated solid copper wires covered with insulation and loosely twisted together. This type of cable was originally used in telephone wiring and is still used for that today, but it is also used for security system wiring or sensors and other equipment. Twisted pair cable is one of the most widely used type of wiring in local area networks. It is generally known as unshielded twisted pair or UTP cable. There are many grades of twisted pair cable for handling low frequency audio or high frequency pulses. The size of the wire, type of insulation, and tightness of the twist determine the characteristics. It is available with an overall braid shield and is called shielded twisted pair cable. Transmission lines can be balanced or unbalanced. A balanced line is one in which neither wire is connected to the ground. Instead, the signal on each wire is referenced to the ground. In an unbalanced line, one conductor is connected to the ground. Open wire line has a balanced configuration. A typical feed arrangement is shown. The driving generator and the receiving circuit are center tapped transformers, in which the center taps are grounded. Balanced line wires offer significant protection from noise pickup and crosstalk. Because of the identical polarities of the signal on balanced lines, any external signal induced into the cable appears on both wires simultaneously but cancels at the receiver. This is called common mode rejection, and noise reduction can be as great as 60 to 70 decibels. The next figure shows an unbalanced line coaxial cable. Coaxial cables are unbalanced lines. The current in the center conductor is referenced to the braid, which is connected to the ground. Coaxial cable and shielded twisted pair cable provide significant but not complete protection from noise pickup or crosstalk, from inductive or capacitive coupling due to external signals. It is sometimes necessary or desirable to convert from balanced to unbalanced or vice versa. This is done with a device called balan from balanced unbalanced. At low frequencies, the transmission line acts as a carrier of AC voltage. For these applications, the only characteristic of the cable of interest is the resistive loss. The size and electrical characteristics of low-frequency lines can vary widely without affecting performance. An exception is conductor size, which determines the current carrying capability and voltage graph over long distances. The electrical length of conductors is typically short compared to one wavelength of the frequency they carry. A pair of current carrying conductors is not considered to be a transmission line unless it is at least zero point 0.1 wavelength long at the signal frequency. Cables used to carry RF energy are not simply resistive conductors, but are complex equivalents of inductors, capacitors, and resistors. Furthermore, whenever the length of a transmission line is the same order of magnitude as or greater than the wavelength of the transmitted signal, the line takes on special characteristics and requires a more complex analysis. Mathematically, wavelength lambda is the ratio of the speed of light to the frequency of the signal f. It is 300 million over f, where 300 million is the speed of light in meters per second in free space or air, and f is in hertz. This is also the speed of a radio signal. At higher frequencies, the wavelength formula is simplified to wavelength is equal to 300 over f, where the frequency is in megahertz. A 50 megahertz signal has a wavelength of 6 meters. By using feet instead of meters, the wavelength formula becomes wavelength is equal to 984 divided by f, where f is in megahertz, while the wavelength is now expressed in feet. The distance represented by a wavelength in a given cable depends on the type of the cable. The speed in a cable can be anywhere from zero point 0.5 to 0.95 the speed of light waves in space, and the signal wavelength in a cable will be proportionally less than the wavelength of the signal in space. Let's try to solve this sample problem. For an operating frequency of 450 MHz, what length of a pair of conductors is considered to be a transmission line? Calculate the physical length of the transmission line 3/8 wavelength long. Wavelength is equal to 984 divided by 450 and is equal to 2.19 feet. Therefore, to be considered a transmission line, it must be at least zero point 0.1 of its wavelength. Therefore, zero point 0.1 times 2.19 is equal to 0.219 feet or 2.628 inches. And to calculate the physical length of the transmission line, 3/8 wavelength long, we multiply 3/8 to 2.19, which gives us 0.82 feet or 9.84 inches. Most transmission lines terminate in some kind of connector, a device that connects the cable to a piece of equipment or to another cable. Connectors are often taken for granted. This is unfortunate because they are common failure point in many applications. Coaxial cable requires special connectors that will maintain the characteristics of the cable. Although the inner conductor and shield braid could theoretically be secured with screws as parallel lines, the result would be a drastic change in electrical attributes resulting to signal attenuation, distortion, and other problems. Thus, coaxial connectors are designed not only to provide a convenient way to attach and disconnect equipment and cables, but also to maintain the physical integrity and electrical properties of the cable. The choice of a coaxial connector depends on the type and size of the cable, the frequency of operation, and the application. The most common types are the PL259 or UHF, the BNC, F, SMA, and N-type connectors. The PL259, which is also referred to as a UHF connector, can be used up to low UHF values or less than 500 MHz, although it is more widely used at HF and VHF. It can accommodate both large and small coaxial cable. Another very popular connector is the BNC connector. BNC connectors are widely used on 0.25-inch coaxial cables for attaching test instruments such as oscilloscope, frequency counters, and spectrum analyzers to the equipment being tested. BNC connectors are also widely used on 0.25 coaxial cables in LANs and some UHF radios. Another variation is the SMA connector, which uses screw threads instead of the cam slot and pin. The SMA connector is characterized by the hexagonal shape of the body of the male connector. Like the BNC connector, it is used with small coaxial cable. The best performing coaxial connector is the N-type connector, which is used mainly on large coaxial cable at higher frequencies, both UHF and microwave. When the length of a transmission line is longer than several wavelengths at the signal frequency, the two parallel conductors of a transmission line appear as a complex impedance. The wires exhibit considerable series inductance, whose reactance is significant at high frequencies. In series with this inductance is the resistance of the wire or braid making up the conductors, which includes inherent ohmic resistance plus any resistance due to the skin effect. Furthermore, the parallel conductors form a distributed capacitance with the insulation, which acts as the dielectric. In addition, there is a shunt or leakage resistance or conductance across the cable as the result of imperfections in the insulation between the conductors. The result is that to a high frequency signal, the transmission appears as a distributed low pass filter, consisting of series inductors and resistors and shunt capacitors and resistors in this figure. This is called a lumped model of a distributed line. Over the length, however, this resistance is responsible for considerable signal attenuation. The effects of inductance and capacitance are considerable, and in fact, they determine the characteristics of the line. An RF generator connected to such a transmission line sees an impedance that is a function of the inductance, resistance, and capacitance in the circuit. We call it the characteristic impedance or the surge impedance, Z sub O. If we assume that the length of the line is infinite, this impedance is resistive. The characteristic impedance is also purely resistive for an infinite length of line. If the resistive load equal to the characteristic impedance is connected to the end of the line. For an infinitely long transmission line, the characteristic impedance Z sub O is given by the formula Z sub O is equal to the square root of L over C, where C sub O is in ohms, L is the inductance of the transmission line for a given length, and C is the capacitance for that same length. The formula is valid even for finite lengths if the transmission line is terminated with a load resistor equal to the characteristic impedance. If the line, load, and generator impedances are made equal, as in the case with matched generator and load resistances, the criterion of maximum power transfer is met. An impedance meter or bridge can be used to measure the inductance and capacitance of a section of parallel lines or coaxial cable to obtain the values needed to calculate the impedance. Assume that a capacitance of 0.0022 microfarad or 2200 picofarad is measured for a 100 feet of transmission line. The inductance of each conductor is measured separately and then added for a total of 5.5 microhenry. And let's assume that resistance is ignored because it does not enter into the calculation of characteristic impedance. In practice, it is unnecessary to make calculations because cable manufacturers always specify impedance. For line lengths of less than 1 wavelength, characteristic impedance does not matter. The common characteristic impedances of coaxial cables are 52, 53.5, 75, 93, and 105 ohms. An important consideration in transmission line applications is that the speed of the signal in transmission line is slower than the speed of a signal in free space. The velocity of propagation of a signal in a cable is less than the velocity of propagation of light in free space by a fraction called velocity factor, or VF. It is the ratio of the velocity of transmission line Vp to the velocity in free space, Vc. The velocity of a signal in a cable is less than the velocity of propagation of light in free space by a fraction called velocity factor. Velocity factors in transmission lines vary from approximately 0.5 to 0.9. The velocity factor of a coaxial cable is typically 0.6 to 0.8. An open wire line has a velocity factor of about 0.9. And the 300 ohm twin lead line has a velocity factor of about 0.8. The velocity factor in a line can be computed with the expression Bf is equal to 1 over the square root of epsilon, where epsilon is the dielectric constant of the insulating material. For example, if the dielectric constant of Teflon is 2.1, the velocity factor is equal to 1 over the square root of 2.1, which is 0.69. If a lossless line or zero resistance line is assumed, an approximation of the velocity of propagation can be computed with the expression v sub p is equal to 1 divided by the square root of LC, where L is the length uh, or total distance of traveled signal in feet or some other unit of length, and L and C are given in the same unit. Calculating transmission line length. The formula given earlier for one wavelength of a signal in free space is the ratio of the speed of light to the frequency of the signal. This expression, however, must be modified by the velocity factor to arrive at the true length of a transmission line. The velocity factor must be taken into consideration in computing the length of a transmission line in wavelengths. So, we will multiply it to the expression. The correct velocity factor for calculating the correct length of a given transmission line can be obtained from manufacturers' literature and various handbooks. Because the velocity of propagation of a transmission line is less than the velocity of propagation in free space, it is logical to assume that any line will slow down or delay any signal applied to it. A signal applied at one end of a line appears some time later at the other end of the line. This is called the time delay or the transit time for the line. The amount of delayed time is a function of the line's inductance and capacitance, the opposition to the changes in current offered by the inductance, plus the changes in the discharge and charge time of the capacitance leads to a particular delay. A transmission line used specifically for the purpose of achieving delay is called a delay line. This figure shows the effect of time delay on a sine wave signal. The output sine wave appears later in time than the input, so it is shifted in phase. The effect is the same as if a lagging phase shift were introduced by a reactive circuit. To determine the phase shift represented by the delay, the frequency and the period of the sine wave must be known. Transmission line delay is usually ignored in RF applications, and it is virtually irrelevant in radio communication. However, in high-frequency applications where timing is important, transmission line delay can be significant. Some applications require exact timing and sequencing of signals, especially pulses. A coaxial delay line can be used for this purpose. Obviously, a large roll of coaxial cable is not a convenient component in modern electronic equipment. As a result, artificial delay lines have been developed. These are made up of individual inductors and capacitors connected as a low-pass filter to simulate a distributed transmission line. Alternatively, a more compact distributed delay line can be constructed, consisting of a coil of insulated wire wound over a metallic form. The coil of wire provides the distributed inductance and at the same time acts as one plate of a distributed capacitor. The metallic form is the other plate. Such artificial relay lines are widely used in TV sets, oscilloscope, radar units, and many other pieces of electronic equipment. This table summarizes the specifications of several popular types of coaxial cable. Many coaxial cables are designated by an alphanumeric code beginning with letters RG or a manufacturer's part number. The primary specifications are characteristic impedance and attenuation. Other important specifications are maximum breakdown voltage rating, capacitance per foot, velocity factor, and outside diameter in inches. The attenuation is the amount of power lost per 100 feet of cable, expressed in decibels at 100 MHz. Attenuation is directly proportional to the cable length and increases with frequency. Attenuation versus frequency for four coaxial cable types is plotted in this figure. The loss is significant at very high frequencies. However, the larger the cable, the lower the loss. The loss in a cable can be significant, especially at the higher frequencies. Several things can be done to minimize loss. First, every attempt should be made to find a way to shorten the distance between the transmitter and the antenna. If that is not feasible, it may be possible to use a larger cable. When you are considering the relationship between the cable length and attenuation, remember that a transmission line is a low-pass filter whose cutoff frequency depends both on the distributed inductance and capacitance along the line and on its length. The longer the line, the lower its cutoff frequency. This means that higher frequency signals beyond the cutoff frequency are rolled off at a rapid rate. This is illustrated in this slide. It shows attenuation curves for four lengths of a popular type of coaxial cable. It should be clear why it is important to use a larger, lower loss cables for longer runs, despite its cost and handling inconvenience. Finally, a gain antenna can be used to offset cable loss. To summarize this lesson, transmission lines are critical links to any communication system. They can be a parallel wire line, coaxial cable, or twisted pair. The most widely used type of transmission lines is the coaxial cable, while parallel wire line are seldom used today. Twisted pair cable is one of the most widely used types of wiring in local area networks. Transmission lines can be either balanced or unbalanced. It is sometimes necessary or desirable to convert from balanced to unbalanced operation or vice versa. This is done with a device called balan, or from balanced unbalanced. To be considered a transmission line, a pair of current carrying conductors should be at least zero point 0.1 wavelength long at the signal frequency. We also learned that the choice of a connector depends on the type and size of the cable, the frequency of operation, and its application. Over longer lengths, the line resistance is responsible for considerable signal attenuation. The effects of the inductance and capacitance are also considerable. and they determine the characteristics of the line. Also, velocity factors velocity factor plays an important role in transmission line applications. We have also discussed the calculation of the characteristic impedance in various ways. Because the velocity of propagation of a transmission line is less than the velocity of propagation in free space, the line introduces time delay to the signal. Finally, we touch on the specifications of several popular types of coaxial cable.